Okay, I want to start off by mentioning this biography of Albert Michelson, the guy from the Michelson and Morley experiment that established pretty conclusively that the speed of light is an absolute for all observers. It's unusual in that it's written by his daughter. Good biographies are rarely written by family members. Usually they're written by someone quite detached from the subject. But she wrote a very good biography. And it's also interesting, although she's neither a scientist nor an academic, I felt that she really captured academic science and the life of an academic scientist pretty well. And in the process, she described a number of very significant experiments of his and described them pretty well. So this is all something of an accomplishment for someone who is, on the one hand, very personally close to the subject of the biography. That rarely makes for good insight, yet here it does. Yet by training, very remote from the subject's area of expertise. And so I highly recommend the biography of Albert Michelson, Master of Light, by Dorothy Michelson Livingston. All right, also an apology. I realized this morning that, more specifically about 15 minutes ago this morning, that on today's assignment, I made an error. I said that the speed, that the thing was going at 1/5 the speed of light, and then I wrote -2 instead of -0.2. So I will be grading those space-time diagrams leniently. And with that, let's get started. So we're going to be talking about time in relativity. And first, we're going to be working in units where speed is between 0 and 1, or between 0 and -1, depending on direction. Because we're measuring distance in either light seconds, so 1 second multiplied by the speed of light, or the distance traveled by light in 1 second, or light years, 1 year times the speed of light, or light nanoseconds, sometimes light microseconds. And so whatever units we're working in, light goes 1 light second per second. It also goes 1 light year per year, 1 light nanosecond per nanosecond, and so forth. And we're going to be using space-time diagrams. Now, in a space-time diagram, people who do relativity decided that we will put time on the vertical axis and position on the horizontal axis. In Physics 1510, you were probably more used to having x on the vertical axis, or distance on the vertical axis, and time on the horizontal axis, in which case your slope is delta x over delta t, or the velocity. But here in relativity, our slope will be delta t over delta x, or 1 over the velocity. That's just one of the quirks of this field. Another thing we're going to have to get used to is that they give these graphs weird names. They call them world lines. Again, it's one of those things we're just going to have to accept. So everything looks flipped around. Oscillatory motion, instead of a sine wave going like this, it would be going like that, right? X, the distance from the time axis, is still oscillating.
We can't see your screen.
Oh, you can't see my screen? I'm so sorry. Okay. All right, let's start that over again. All right, so space-time diagrams. Time on the vertical axis, x on the horizontal axis. Slope is 1 over v, whereas what we were previously doing in all of your physics classes was distance on the vertical axis, time on the horizontal axis. So your slope would be delta x over delta t, or velocity. Now your slope is delta t over delta x, or 1 over the velocity. And that is sadly something we're just going to have to accept. So everything gets reversed. Oscillatory motion now looks like this because you swap the axes. Accelerated motion. You were used to a parabola taking off like that. Well, it's still a parabola. It's just been flipped around, so now it goes like that. If we look at constant velocity motion, well, we still have straight lines, except those straight lines are always going to be close to the vertical axis because the slope has got to be larger than 1 so that the speed or velocity 1 over the slope can be less than 1. And then stationary objects, before you would have something constant. You would have that the position as a function of time is a flat line. Well, now the time as a function of position is a vertical line for a stationary object. That's just the way they do things in relativity. I don't know what Einstein came up with this, but that's how it is. All right, so the world line of light is going to have a slope of either 1 or -1. So let's look at an event where light pulses are emitted to the left and to the right. The ones going to the right travel with a slope of +1. Ones going to the left travel with a slope of -1. And if event A is the emission of the light and event B is the detection of the light by something sitting over here, then we want to figure out when event B happens. So we're going to say that event A occurs with time coordinate 2 microseconds and x coordinate 4 microseconds. And remember that a microsecond as a distance unit is just going to be a microsecond multiplied by the speed of light, or 10 to the -6 seconds multiplied by 3 times 10 to the 8th seconds. So we're going to be talking about 300 meters. All right, so 1 microsecond is 300 meters. This would be 1,200 meters. And we want to know what are the time and position of event B. Well, we're going to say that the coordinate of the detector is 2 microseconds. All right? So right away, we can figure out the position of event B. Event B is going to happen when x equals 2 microseconds. And then we have to figure out the time. Well, constant velocity motion is still simple. We have this tendency in physics to tell you how wrong your intuition is. I think I've ranted about this before. In short, in 1510, spend a whole lot of time giving you demos where things are counterintuitive and we emphasize what's counterintuitive. Then in relativity, things are even more counterintuitive. So once you finally start to develop some kind of intuition that we will deem acceptable and stop tearing apart for Newtonian physics, suddenly we laugh and say, ha, well, now you have to deal with relativistic intuition. But not everything goes against your intuition. Constant velocity motion is really simple. X is just the starting point plus the velocity multiplied by how much time has elapsed. So the coordinates of this light going to the left will be XA, because that's where it started from, plus -1 or minus, because remember, this light is going to the left. So because this light is going to the left, its velocity is -1. If we're going to the right, it would be +1. And then T minus TA, how much time has elapsed since it started traveling? You might be thinking, well, shouldn't it just be T? Well, it would be T if it started off at T equals 0. But it didn't start off at T equals 0. It got emitted at T equals 2 microseconds. So X light equals XA minus this interval. So we can solve for when that intersection happens by setting the coordinate equal to 2 microseconds. Remember that 2 microseconds is the position of the detector. That's equal to 4 microseconds, the starting position, minus TB minus 2 microseconds, where that's the time interval. Or 4 microseconds minus TB plus 2 microseconds, because we got minus, minus. 6 microseconds minus TB equals 2 microseconds, or TB equals 4 microseconds. Why did I write 2 there? That was a mistake. Anyway. So that's how we would do a problem like that. Any questions on what I just did? All right. Now, let's talk about reference frames. I said last time we're going to have a convention where what we call the home frame is usually someone who we can regard as standing on the ground. It's someone who we would feel very comfortable in our intuition saying is standing still. Now, we have to be careful because in relativity, there is no such thing as a person who is definitely standing still and a person who's definitely moving, because the laws of physics are the same in all reference frames. So as far as one person's concerned, everyone else is moving. But for convenience and trying to think about these things as a human, we'll put the home frame in some context where it seems reasonable to say, yeah, this person's standing still. And then the other frame will usually be the person who it's most natural to talk about as moving. And this is usually the case. Sometimes we'll flip things around. So the other frame would be someone on a train, and they're going right with respect to the person on the ground. We're going to call their velocity beta. Beta is just a common symbol for velocity and relativity. Don't ask me why. And we're going to usually say that the other frame is moving to the right because that way we have positive numbers, negative numbers, make it easier to make mistakes. So the other observer, according to someone in the home frame, their world line looks like this, and the slope is 1 over beta. Conversely, even though I said that we're going to often talk about things from the home frame perspective, as far as the person on the train is concerned, if they're going at a constant velocity and moving smoothly, they don't feel any jerking or shaking, they think they're standing still, and everyone else is moving. If you've ever spent much time on trains, if you've ever been in a place where you ride the subway, when you're on a subway car, especially in a tunnel, it's a little bit different outside. You've got all these visual cues of people and trees and buildings. And so much like you're used to in a car, you have an intuition that, oh, my car has started moving. We don't have a lot of intuition for moving walls. So when you're in a subway tunnel, when you're in a subway station underground, and this train starts moving, you may feel your body jerk, but you look out the window and all you see is a moving wall, okay? And so you're not accustomed to moving relative to walls. You may be thinking, sure I am. I walk around inside my house since God knows I'm not allowed to go outside these days. But we don't have a lot of intuition for being in a seated position while walls move. And so or in a seated position while we move with respect to walls. So it looks like the walls of the subway tunnel are moving. The first thought in my brain before I stop myself is, oh wow, those walls are taking off. Anyway, the result is that the home frame observer, the home frame observer looks as though they're moving to the left according to the other frame observer. And the slope of that line is -1 over beta. Now, some of you may be thinking, well, why is it -1 over beta instead of something else? In relativity, there's a few things you're allowed to agree on. We may disagree on all sorts of things. We may disagree on time and position measurements, but there are 3 things we can all agree on in the theory of relativity. We can agree on the speed of light. We can agree on our relative velocity. I might think that our relative velocity is positive, while you think it's negative, because we're going to disagree on who's going left, who's going right, who's standing still. But at least we'll agree on the magnitude of our relative velocity. The person on the ground thinks that the train is moving to the right at 30 meters per second. And the person on the train thinks that the person on the ground is moving to the left at 30 meters per second. So they agree on the magnitude of their relative velocity. The only thing they disagree on is the sign. And then finally, of course, all observers in relativity agree that motion is impossible on the 405 freeway. Okay, So if we synchronize clocks, let's talk about what it means for clocks to be synchronized. I said that last time, a reference frame could be defined as just a whole bunch of different clocks that receive light at different times, that receive light and they're evenly spaced, and they record the time at which they receive the light. So let's imagine that we've got an event that we call S, and it happens at the origin. Someone emits a pulse of light in both directions. Each of these clocks is going to receive the light at a different time. And the time at which they receive the light will be X, the distance from the origin, over C. So all these clocks are going to receive light at different times, but they all agree on when the light was actually emitted from the origin, because someone standing over here will say, oh, well, I was, I don't know, 50 microseconds from the origin. And I know I'm 50 microseconds from the origin. That was all worked out when the clock was positioned here. And my clock reads 50 microseconds when the light was received, so it must have been emitted at t = 0, all right? And this person over here, they're 10, 20, 30, 40 microseconds to the left of the origin, so their clock reads 40 when the light is received, but they all agree that, hey, you know, I'm getting this at t = 40. That means that the event happened at t = 0 because we've got some information that this light was emitted from the origin. Any questions so far? Then let's switch to some of the questions from the end of chapter 2. For each of these questions, I'm going to give you a little bit of time to think about it, and then we'll discuss. So imagine that in the distant future, you're on Earth and you're watching a transmission from Pluto, and that's 5 light hours from Earth. And as you're watching this video from Pluto, you notice that a clock on the wall behind the speaker reads 12:10 p.m. And your watch also reads 12:10 p.m. So, is the clock in the Pluto space station synchronized with your watch? Let's take a moment to think about that. All right. Now, I'm not going to bother to do the voting that I would do in class because I haven't set up an app for that. But let's just look at the answer to this question. They are not synchronized. The reason why they are not synchronized is because if they were synchronized, well, then right now, yes, on Pluto, their clock would also be reading 12:10, but you're not looking at what happened on Pluto right at this moment. You're looking at what happened on Pluto 5 hours ago. So their clock should be reading 7:10 a.m. Any questions? All right, we receive a message from some distant base 13 light years from Earth. It's dated July 15th, 2127. What year does your calendar indicate if your calendar and the space station's calendar are correctly synchronized? Take a moment to think about that. Right. Yep, 2140, as a few people say. And the reason, of course, is it takes 13 years to get there. So they would have sent it in 2127 and it arrives 13 years later. Okay, now, in these units that we're working in, what is the speed of a car on the freeway? And assume that it's like the 10 freeway when there isn't much traffic, not the 405 freeway where the speed is always 0, but the speed of a car on the 10 freeway when there isn't much traffic. Think about what that would be in relativistic units. Whoa. Correct answer is A, 10 to the minus 7. Why does my computer do that? Okay, because the speed of a car is going to be 10, 20, 30 meters per second. If you put 10 to the minus 8, so that you said 10 meters per second, well, that would be more like a city street. It's going to be about 20, 30 meters per second. So we take, 20 or 30, maybe 3 times 10 to the 1, divide by 3 times 10 to the 8th. We get roughly 10 to the minus 7. If you said 10 to the minus 8, I get you. If you said 10 to the minus 6, well, I don't really want to be driving. Let me know what time you're leaving campus. I'm going to leave campus at a different time once we're all allowed to go to campus again. Okay, now let's say you're sitting at the origin of an inertial reference frame, and at t equals 80 nanoseconds, you received the light from an event which occurred near a clock at x equals minus 30 nanoseconds. So when do you observe that the event occurred? As far as you're concerned, what time did the event E, the emission of the light, occur? Take a few moments to think about it. "50 nanoseconds." Because the event happened 30 nanoseconds away. So it's going to take 30 nanoseconds for the light to reach you, all right? Which means it must have happened at t equals 50 nanoseconds. By the way, let's think about what 30 nanoseconds would be. The speed of light is 3 times 10 to the 8th seconds. And if we multiply by 3 times 10 to the minus 9, well, 30 times 10 to the minus 9. Well, first we multiply by 3, and we're going to get 9 times 10 to the 8th. Then we're going to multiply by 10, and we're going to get 9 times 10 to the 9th. And then we're going to multiply by 10 to the minus 9 for nanoseconds, and we're going to get 9 meters, all right? 9 meters is, the size of maybe a large room. It's very human scale distance. Also, nanoseconds, I've worked with lasers that produce nanosecond pulses of light. It's not hard to produce nanosecond pulses of light. Nowadays, people produce light pulses that are way shorter than that. They produce picosecond and femtosecond pulses, even attosecond or below. So 30 nanoseconds, that's a large room. And a few nanoseconds would be roughly the amount of time between when a lot of atoms will absorb light and then when they will re-emit the light. Again, that's typical. There are plenty of atoms and molecules that absorb and re-emit much faster, plenty that absorb and re-emit much more slowly, but That would be typical. Any questions? Okay, now here's a bunch of world lines. At t equals 1 second, which object has the largest speed? So look at each of these world lines and think about how you work out the speed of an object based on the world line. And then at t equals 1 second, tell me which one you think that is, A, B, C, D, or E. All right, I'm going to show it. A, because A has the smallest slope at t equals 1 second. Remember that the velocity is 1 over the slope. And if I'm only looking at t equals 1 second, now we could talk about E in a moment. If we leave aside E, well, this one's almost vertical, so that's got to be very close to 0. This one is most definitely non-vertical, and this one is most definitely non-vertical. But this one has a smaller slope. It's a little bit closer to the horizontal, so it's going faster. Now, E, two things about E. First of all, E is impossible because its slope is 0, which means its speed would be infinity. That doesn't make any sense. Second of all, even if we were to somehow talk about an object doing this, well, at t equals 1 second, I don't see this line anywhere. If I only look at t equals 1 second, we've got something that's everywhere at t equals 2 seconds. Any questions? Okay, now let's talk about t equals 4 seconds. Which one has the largest speed? At 4 seconds, I would accept A or B. I feel like we could have a debate between A or B. The textbook author says B, but I would accept A or B because remember, all of this is qualitative, reading it with our eyes. We didn't take out rulers for this. And we already talked about which world line could not possibly be correct, E. Okay, true or false? The object whose world line is labeled B is moving along the x-axis. Yeah, looks true to me. I mean, the x-coordinate starts off decreasing slightly, then starts to increase, but that is definitely motion along the x-axis. All right, and finally, a light flash leaves a clock at the origin at t equals minus 2 seconds. It gets reflected from an object a certain distance in the x direction from the origin, so somewhere to the left of the origin, and then returns to the origin at t equals 8 seconds. So from this information, what must the space-time coordinates t and x, remember the first number here is t, and the second number is x, what must those space-time coordinates be for that reflection event? So I'll give you a minute to think about that. And remember, this is light. talk about why this is. It was traveling for 20 seconds. It left at t equals minus 12, returns at t equals 8. So 8 minus negative 12 is the same as 8 plus 12, or 20. So it travels for 20 seconds. So for the first 10 seconds, it was going to the left, which means that the position of that event must be minus 10 seconds. And then it narrows it down to these two, and then we just have to remember that 10 seconds after negative 12 is negative 2, not plus 2. Any questions? Okay, so let's look at another problem from the book, not one of the 2-minute problems. We have 2 radar pulses sent from Earth at 6 a.m. and 8 a.m. And they bounce off of an alien ship and return at 3 p.m. and 4 p.m. But we don't know which pulse is which. We just know that there's a pulse left leaving Earth at 6 a.m. So the world line of that pulse looks like this. And there's a pulse leaving at 8 a.m. So its world line looks like that. And we get pulses at 3 p.m. and 4 p.m. So we know that anything that reached Earth coming from the right at 3 p.m. has a world line with slope. Well, it was traveling to the left, so its slope is negative 1. It's going like this. And anything that reaches Earth at 4 p.m., it's going to the left, so its slope looks like this. And then we just have to figure out what is the speed of the alien ship. Well, here's the thing. There are 2 intersections between this pulse and the pulses leaving Earth. And there are 2 intersections between this pulse and the pulses leaving Earth. And we're going to say that we don't know exactly when those pulses were sent. I suspect that in reality, a radar pulse would have some sort of timestamp on it. You know, that it wouldn't just be a simple identical pulse sent every hour or 2 hours or whatever, but there'd be some sort of modulation. So what you get back will have a timestamp of when it was sent, but we'll leave that aside for now. Well, we don't know a priori when the 3 p.m. pulse intersected the alien ship, and we don't know a priori when the 4 p.m. pulse intersected the alien ship. The alien ship could have followed a trajectory that goes from here to there, or it could have followed a trajectory going from here to there. Except if it followed this trajectory, its world line would be very close to flat. And if its world line is close to flat, then its speed will be greater than 1. And we're assuming that aliens obey the laws of physics because this is physics class, not a science fiction movie. And so if it's physics class, then the alien ship has to obey the laws of physics. So it could only be going like this. And then we could work out the time at which each of these things could happen. Okay, so pulse 1, the one that left at 6 a.m., comes back to Earth at 3 p.m. So that's a 9-hour round trip. So it went 4.5 hours away from Earth, hit the alien ship, came back. Then the second pulse went from 8 a.m. to 4 p.m. That's an 8-hour round trip. So it went 4 hours each way, right? So the alien ship, when it received the first pulse, was 4.5 hours away from Earth. And when it received the second pulse, it was 4 hours away from Earth. So it traveled half a light hour. Now that first pulse had to hit the ship. If we just work out, well, 4.5 hours after 6 a.m., that's 10:30 a.m. Second pulse, 4 hours after 8 a.m., that's noon. So an hour and a half passed between when the first pulse of light hit the alien ship and when the second pulse of light hit the alien ship. So it traveled half a light hour in 1.5 light hours. Its velocity, its speed is c over 3. Its velocity, I actually should have put a minus sign, it's approaching Earth. Any questions? Anyone? Going once, going twice, 3 times, sold. Okay, here's the central mind-bending paradox of relativity, which is that the time interval between 2 events depends on your reference frame. So let's imagine that this person in the other frame, the person on the train, has in the center of their train car a firecracker. And the firecracker explodes at x prime equals 0, the center of the train car, and at t prime equals 0. Pulses go to the right and to the left. There's light traveling both directions in the train car. If it's in the center of the train car, we have 2 detector clocks on the left and the right, equidistant from the center. It'll take the same amount of time, as far as someone on the train is concerned, to get from the center of the train car to the right side or the left side, okay? Because as far as the person on the train is concerned, well, that light traveled at the speed of light, and those 2 events are simultaneous. Now, if you have any questions at all about this diagram, ask them now, because we're about to jump off the deep end. So ask your questions now before we jump off the deep end. Okay, we jump off the deep end. Let's talk about the person on the ground. The person on the ground, their origin lines up with the person on the train. We could think that the person on the ground, the train car just happened to pass by them at the instant that the firecracker went off. So the person on the ground looks and waves at the person inside the train car. They're standing right opposite to each other, okay? So if I'm right in front of my camera, we could imagine that I'm the person on the train and you are looking into your screen and you see me and we line up exactly when the firecracker goes off. Now, the person on the ground says that light travels to the right, light travels to the left, and it's going at a speed of 1. So this line has a slope of +1, and this line has a slope of -1, all right? But the person on the ground also says that, hey, this clock on the train is going to the right. So it's going to take the train a little bit longer to catch, it's going to take the light a little bit longer to catch up with it. Just hang on to that. We'll get to that in a second. Meanwhile, the person on the ground says, hey, this clock is rushing towards the light. The clock on the left is rushing towards the light because the train is going to the right. So it's not going to take as long for the light to reach that clock. Now you may be thinking, wait, I thought that the light always goes at a speed of 1. The answer is yes. Light always goes at a speed of 1. As far as I'm concerned, all right, I see light traveling at a speed of 1 relative to me. As far as you're concerned, you see light traveling at a speed of 1 relative to you. But that doesn't mean that I see light going at a speed of 1 relative to you. I see light going at a speed of 1 relative to me. I don't see light going at a speed of 1 relative to you, right? To put this in perspective, let's suppose that we had astronauts on the moon, and we hopefully will someday again. And we worked something out. We were going to do some sort of precision timing experiment, which is actually plausible, that the person on the moon is going to send out a radio pulse at a prearranged time. And we're going to see when that radio pulse reaches the equator on the side facing the Earth. And we're also going to see when it reaches the North Pole. We're going to have detector stations at the equator and the North Pole. Now, it's going to take a little bit longer to reach the equator than, it's going to take a little bit longer to reach the North Pole than to reach the equator. So the person at the North Pole knows in advance when they have to be there, okay? They have some time. They have slightly more time to get their detector in place. In reality, the amount of extra time they have to get it in place is just a tiny fraction of a second. But still, they've got that time. So the person at the North Pole could be scrambling to move their detector into position in that final little fraction of a second, okay? And as long as they get there by the prearranged time, as long as they get their detector into its exact position by the prearranged time, they will have caught up with it. Meanwhile, the person on the moon, they've got all sorts of information. They might know that the detector is in motion. They might know that the person at the North Pole lab is a procrastinator and is not going to get their detector into position until quite literally the last nanosecond. Okay, so the person on the moon could know in advance that, hey, this detector is going to be in motion and the light that they're sending from the moon is going to be in motion, all right? So I can see light going at some speed other than one relative to you. But I can only see light going at a speed of one relative to me. So the person on the train says, here's the world line of the light. Here's the world line of the other light pulse. Here's the world line of one detector. Here's the world line of the other detector. And these two events, the light arriving at the detector on the left and the light arriving at the detector on the right, occur at two different times in the reference frame of the person on the ground. So what looks simultaneous to someone on the train looks like it happened at two different times to a person on the ground. And it gets even weirder. The person, if the train had been going in the other direction, the order of those two events would get flipped. And if we had multiple detectors on the train, some of them very close to the center of the train on either side, some of them further off. Now, of course, the person on the train would say that light got to each of these clocks before it got to each of these clocks, the far out ones. But the time lag, according to the person on the ground, is larger for two events that are farther away from the origin. So I've just thrown a massive piece of weirdness at you. Ask your questions. I know you've got some. Get to that one later. Somebody must have a question. This is super weird. Yeah, that is. I see in the comments that in the group chat, that is one fast train. But one thing that's tempting is people think that, oh, well, this just has to do with when light arrives, when we see things. I'll get to you in a second, Ben. People think, oh, that's just when we see things. That's not when things actually happen. No, that is when things actually happen. I mean, the light, according to a person on the ground, all the evidence, any experiment that a person could do on the ground, setting up detectors everywhere, as long as they're stationary with respect to the person on the ground. You could have detectors everywhere along that train track. You could have cameras looking into the windows of the train, cameras every inch, along every inch of that track, looking through the windows of the train whenever the train passes by. They would all say that this event, the light reaching the detector on the right side of the train, happened after this event, the light reaching the detector on the left side of the train. Ben, you had a question.
If you were traveling at light speed, light would still be traveling at light speed for you?
I don't know how to answer that question because no material object, no object that has mass could reach light speed. It would take an infinite amount of energy in order to reach light speed. So the only way that could possibly happen is maybe when my little nephews were toddlers and they had an infinite amount of energy. But at that age, they are qualified to work as physics lab technicians. But all jokes aside, in order to detect light, some material object has to receive the light, receive the energy from the light, and undergo some sort of change, whether it's a chemical reaction, whether it's the light causing a little spark of electrical current. Something has to happen. And we can't get a material object to the speed of light. Now, at this point, after I say that we can't have things go at the speed of light, the usual question I get is, but what if hypothetically you could go at the speed of light? And here's my honest attempt at an answer, and I really don't mean this to be cruel. But what you're asking me is what the laws of physics would be if they weren't what they are. And the answer is I don't know. Right? The laws of physics as they currently are, as we know them, the laws of physics as we know them in the universe that we exist in, do not allow material objects, objects with mass, to go at the speed of light. If the laws of physics were different and something could go at the speed of light, well, then I'd have to know what those different laws are before I can answer that. Other questions? Anyone? Okay, now let's ask this question. What if the person in the home frame, the person on the ground, saw the light reach both detectors simultaneously? Okay? Well, if the person on the ground saw the light reach both of those detectors simultaneously, according to the person on the ground, one of those detectors is going to the right like this, and the other one is going to the right like that. So if both of those events happen simultaneously, they have the same time coordinate. So I could say, okay, at this position, a light pulse reached this position at this time. Let's figure out when that light pulse must have left the center of the train. Now, oops, I marked the wrong points on here. This is what happens when you're doing your notes pre-prepared rather than writing on a board. Okay, so the person says, all right, there's a light pulse going to the right. Well, it must have intersected the center of the train at this time. So it started from the center of the train at this time. There's a light pulse going to the left. It must have started at the center of the train at this time. Not this one, ignore that. It must have started from the center of the train at this time, okay? So even though these two events, light reaching the left and right sides of the car, are simultaneous in the home frame, the person in the home frame is forced to conclude that these two pulses of light were emitted at different times on the train. Any questions? Anyone? If you take nothing else away from today, take away that we can use space-time diagrams to follow light and figure out when it must have left from a given source in order to reach a given detector. And that when we do all of that, we are forced into the bizarre conclusion that events that are simultaneous in one frame are not simultaneous in another frame. Next time, what we will do is we will start trying to actually calculate, okay, given that people disagree on time, we established today that they disagree on time, well, what amount of time do different people measure? How much time does one observer measure? How much time does another observer measure? Now, I found 2 mistakes in today's notes. I'm going to correct those as soon as I log off. Then I'll post corrected notes. I will post the answers to all those questions from the 2-minute problems at the end of the chapter. And I will also grade the assignment that was due today, and I will be lenient since I put v equals -2 instead of -0.2. Any final questions? All right, remember that tomorrow at 4 p.m. I'm going to hold an online review session to go over homework questions and last semester's midterm, because we have a midterm this Friday. Have a good day.